I have been working with Roshana Karamova in Professor Isaac Smith's lab for the past year in order to develop an experimental setup to simulate the Martian polar climate. Mars is a planet of great interest as it is home to a multitude of atmospheric and surface processes that have no comparable phenomena seen on Earth. Such includes the interacting water and carbon dioxide volatile cycles. The CO2 cycle in particular lends itself to condensing up to 30% of the entire atmosphere into ice sheets in the polar regions of Mars. CO2 ice can form in a wide variety of different textures given minute changes in the pressure and temperature of the surrounding environment. These textures within the ice can change when exposed to light, altering the optical properties of the ice. This change can have a large impact on factors such as the planetary albedo and the energy budget of the planet. The effects of light on CO2 ice can also create very interesting surface features. Such includes jets of dirt and regolith. These jets form when the bottom layer of a transparent CO2 ice sheet is warmed and sublimates, forming high-pressure CO2 gas streams underneath the ice. The gas is able to pick up loose substrate on the surface and eventually finds a weak point in the ice through which the high pressure is relieved. The formation of these jets, as described by the Kiefer model, lead to the creation of negative relief channels, or more commonly referred to as spiders. In order to further study these phenomena, we have designed an experimental setup to recreate the environment in which the ice forms. Proof of this concept was demonstrated last summer when a basic system with rudimentary pressure and temperature control was installed, allowing us to successfully condense ice from a CO2 atmosphere and photograph the growth. The pressure and temperature control systems of this design were completely analog and did not allow for fine-tune adjustments. Our new setup has made several improvements, the most prominent of which is a new, larger vacuum chamber dedicated to the purpose of creating planetary ices. The interior walls have been painted with a high emissivity black in order to mimic the black body radiation conditions. The thermal control of our system has also been improved. Previously, issues arose in our experiments when the CO2 atmosphere would be significantly warmer than the cooled surface that the ice was depositing onto. This formed a very dramatic thermal gradient, causing internal stress and fracturing in the ice sheets. In order to alleviate this, the new chamber has a platinum shroud cooling system, allowing for the atmosphere of the chamber to be cooled individually from the deposition plate. The deposition plate has also been upgraded to include an electronic heater. This heater allows for finer control and minimizes the unpredictable effects of hysteresis that liquid nitrogen often suffers from. Thermal control has also been automated. By taking readings from the thermocouples placed strategically around the chamber, the heater and liquid nitrogen flow are adjusted automatically to meet user-specified temperatures within 1 Kelvin. This setup allows for the addition of multiple deposition plates, should we choose to produce and study more than one sample of CO2 ice at a given time. The pressure control system has also received an upgrade to its precision. The use of a mass flow controller allows us to know exactly how much CO2 is inside the chamber at any given time. The addition of a capacitance manometer provides us with a very accurate pressure reading, regardless of the gas composition inside of the chamber. These systems are currently being automated as well to allow for continuous pressure management for experiments that may extend for longer than a few hours or a day. All of our automation is being done through National Instruments LabVIEW in conjunction with supported electronic control devices. This has been my main focus over the summer, as it is easily transferable to a work-from-home environment. LabVIEW allows for the design of simple user interfaces, making it much easier for the researchers to focus on their experiments rather than on the intricacies of operating the equipment. Once we regain access into the laboratory, we will be able to install the remaining components onto the chamber and connect the system to the computer. Once the installation is complete, it will be simple to remote into this setup, minimizing the need for human intervention. Our first priority of research will be to measure and confirm the existing measurements of the reflectance of CO2 ice. Other experiments will take place in the chamber in the future, such as trying to recreate certain stages of the Kiefer model. Continuous support for the LabVIEW program will be necessary in order to provide the researchers with the smoothest possible experience.